talk about this work I made together with Jacopo and with Maciek and Milos from Warsaw. This work is also related to some results we found together with Friedrich and Benjamin that are here. So the main character of this work will be integrable models that, as you know, have an infinite set of conserved charges that in particular are local or quasi-local, and I will call small qi the density of these conserved charges. And at equilibrium in particular they are described by this generalized Gibbs ensemble. We are also interested in out-of-equilibrium dynamics, in particular in coarse-grained dynamics that I will call hydrodynamics. So always scale time and space by this factor L. And the powerful of this theory is that assuming local entropy maximization in each fluid cell, we can rewrite the hydrodynamic equation for the normal modes that will be nothing else than the density of the average densities of these conserved charges. And at this point we can rewrite typically the density of currents in terms of an expansion of density of charges. And we can find an infinite tower of equation that must be solved together. In general, this equation cannot be solved together since we have an infinite set of conserved charges, but we can recast them into a unique equation for quasi-particles where we exchange this index I with a continuous index theta that is nothing else than rapidities of our quasi-particles that is strictly connected to the momentum of these particles. So this has a very nice physical interpretation. In fact, this infinite tower of equation recast into a unique, pretty simple Euler scale dynamic equation where we have a ballistic transport with an effective velocity that is dressed due to the interaction with all the other particles in the system. In particular here, I took a very simple case, the hard sphere gas, where in one dimension this particle can simply exchange their momentum, and so all the set of initial momentum is conserved in the dynamics. And we can see here the dynamics of a single particle. We can see that the bare velocity of the single particle is not capturing the real dynamics of this trajectory. But indeed the effective velocity is the correct average dynamics of this test particle. So this theory also can be extended to the presence of some smooth integrability breaking taps, where, for example, we can couple this tap to the density of particles, you see. And assuming that this tap is smooth, so is acting globally on the system and not locally inside a single fluid cell, we can write an evolution equation for this dynamical system. And in general, we are interested in some situation like the Kinoshita famous experiment. So we want to observe the dynamics of a system out of equilibrium and understand how this system is eventually thermalizing at large time. So the main motivation for this work is this paper that came out in 2018. In particular, in this work, they have been able to observe an ultra-cold bosonic system of atoms. In particular, they loaded this atom into this quasi one-dimensional geometry. They had different tubes, and these atoms were characterized by a strong magnetic dipole-dipole interaction. So typically ultra-cold bosonic atoms interact effectively with delta function interaction that is integrable in one dimension. And on top of that, in this case, they also had this large-scale interaction due to the dipole-dipole interaction between the atoms. And these atoms are not only interacting inside the same tube, but also within different tubes. So how they analyze this problem was to compute, like to recast the peak of this dipole-dipole interaction inside the same atom as addressing, as a contribution to the delta peak for the interaction. So they had a contribution also coming from the DDI interaction. And at the end, they found that this gas was interacting with an integrable interaction that is the same as the deep linear, and then on top of that also with a large-scale interaction that was decaying with the cubic of the distance between particles, again, both inside the same tube or in different tubes. And they observed the dynamics of density of momentum of these atoms inside a single tube, and they observed that this density was relaxing to the thermal density. So the system was effectively relaxing at long time. And in particular, they found the determinization time scale for this dynamics was quadratic with the integrable interaction, but also quadratic with the dipolar interaction. In particular, there was no theory explaining why they found this determinization time scale, and this is the reason why we started to analyze this problem.
So, sorry, how did they find this? They were able to tune both of these parameters in the experiment?
Yeah. They had one parameter that was this angle, that is the angle of these tubes. So when you tune it, you can change the dipole-dipole interaction. So you can change both the integrable, the parameter in front of the delta, and you can change also the parameter of the dipole-dipole interaction, the large scale. So we will consider from now this setting. So we have an Hamiltonian that has an integrable component, and on top of that, an integrability breaking two-body interaction that for simplicity is coupled to densities. And the main assumption is that this interaction is by definition at large scale. So this is acting on scale psi that is also fixing our aerodynamic scale. So we will always observe space and time on scales that are proportional to psi. And okay, by now we don't have any precise assumption on how this function must decay, but we will consider always like polynomial decaying of this interaction. But it can be also truly long range, like never decaying. It's not a problem. So similarly to what we see also in the experiment, these resemble also some more general setting, like the one-dimensional Lennard-Jones potential that is the archetype model for intermolecular interaction, where, for example, here we can model the Pauli repulsion as a hardcore interaction between particles that in 1D is integrable, and on top of that we can consider the dipole-dipole interaction as our large-scale interaction. So we aim also to model a more general class, more large class of models. So before entering to our theory, I would like to say something about the BBGKY. That is like the most simple way to study the evolution of an interacting system, at least classical. So in BBGKY, people typically consider a classical gas of particles with a two-body interaction. These are, of course, the Hamilton equation, and this is the microscopic density of particle. And what people do is to derive the evolution equation for the average density and average also correlation function at any correlation function. So you have to do some calculation. You have to consider a few point function and then remove the disconnected part. There is a full theory that explains that. And at the end, you can find a hierarchy of equation for the connected correlation function that I will call Gn, for example. This is the connected two-point function. What you find is that these equations, all of them are connected, and you need to truncate this hierarchy somehow. The most to consider a weak potential, and then we have an ordering for endpoint function. So in this case, the three-point function will be higher order. You can neglect this term, and then you have a closed set of two equations. What you can do is to put them in the computer and then compare it with your simulation. And everything is simple, but in 1D we have something more interesting. In fact, in 1D, even these two couple equations, they do not thermalize. If you solve them, you will not see a final Gaussian distribution for the velocity of particles. And in fact, also for long-range interacting system in homogeneous setting, the kinetic equation like Landau or Denner-Balescu, they vanish. This is simply a consequence of the geometrical constriction that you have in 1D, because in 1D, if you have only a two-body interaction, you can only exchange the momentum of particles, while in many dimensions, this set of momentum is not conserved. So in 1D, if you want to observe a thermalization from a two-body interaction, you need a three-point function entering in the game. So you need also to consider this term.
So at the moment, for just keeping the first two orders, is that equivalent to Boltzmann equation, or
what?
Just truncating at this low order, is that equivalent to the Boltzmann equation?
What is equal to Boltzmann? Okay, if you compute Boltzmann equation, if you compute a non-vanishing Boltzmann equation, then you need to consider also the three-point function in order to get a gain. So if you consider the three-point function, then you can compute a kinetic equation for this set of three equations.
How resolve the three-point function in terms of the lower order functions?
You can use some approximation.
Right.
Yeah, and yeah.
Okay, so it's a different sort of truncation.
Yeah, and then like this kinetic equation will be the same as your Boltzmann equation in the limit of small k. So at the end you find the same result. This kinetic equation was derived in these two papers. And in particular, for this system, the thermalization time scale will be proportional to the 4 power of the potential. So, like phenomenologically, you will find some system that will relax at extremely long time scales, and will present also some prethermal state. So now let's introduce also integrable interaction into the game. So I will merge together integrability, BBGKY, and the dynamics to find some hierarchy of equation for this system under the usual assumption that this potential is large scale. This is crucial. So the first important thing to say is that now we don't local GGs are not enough to describe the system, because we have also some correlation that are playing a fundamental role. So we need to extend it, including not only inverse temperature, but also some few point function. And this is not a new idea. This was already introduced in this other recent paper, and like we had confirmation that this is correct. And in particular, these few point function are strictly connected to the correlation function that will be the fundamental fields of our theory. So we will find some dynamical equation for these functions, nothing else. So the main step is pretty simple, and it's to compute the microscopic evolution equation for the single charge density by taking the Heisenberg equation. And so you have the commutator with the integrable Hamiltonian that is giving us the current, and then the commutator with the interaction that is giving us a two-point function. And already we can see the hierarchical structure, because here we have two functions and here only one. After that, we need to take the average of this object and to start building few point objects. Now we have some difference between this theory and the standard BBGKY theory. And the first one is that these currents are not simply linear in the charge, but we need to consider also higher aerodynamic projection. This is already an idea already introduced in this paper and also in other works. And this is not only to do for a 1-point function, but also for a 2-point function and so on. And okay, these are it's not two. Here we can see that if you consider the higher projection of current of 2-point function, you will find a 3-point function. Here you have 3 points. This is wrong. Okay, then there is another more technical thing to consider is that typically in integrable system at a dynamic length scale, when you consider the connected few-point function, you have some non-trivial singular contribution. For the 2-point function, this is nothing else than the susceptibility matrix of the system. But for a higher point function, you have higher object that you need to compute. In particular, this object with the curly bracket that I introduced here, they are not fundamental fields, so they will have some functional dependence on the fundamental fields that will be the few-point function without curly brackets. So the last main difference between this theory and BBGKY theory is that here we need two parameters to truncate the hierarchy, because we are considering a small, like weak interaction potential, but also like a dynamic expansion. So in general, we are considering homogeneous system because it's more interesting to look at thermalization for this kind of system. And in this case, we will always have 1 over psi for 2-point function, so like 1 over psi at the n-1 for any n-point function, but also we'll have some correction due to the interaction potential. And this is true only for homogeneous system. If the system is non-homogeneous, this will be order 1 in the potential. So at the end, this is nothing else than putting together the BBGKY ordering together with the large deviation scaling for a few-point function. So arriving at our equation here is a bit technical, but I will tell you. This is the leading non-vanishing form of this hierarchy. So let's start commenting. We have a 1-point function that doesn't have any ballistic propagation and so on because it's homogeneous, so it's pretty simple. It's simply depending on the 2-point function. So we need to solve the equation for the 2-point function, and here we see that we have some diffusive-like evolution. This is a ballistic propagation. This A is a rotation of effective velocity, and here it's depending on the 3-point function, but now not because of the long-range interaction, but because of the integrable interaction. And then we have some forcing that is depending on only on the density. And the 3-point function is coming purely from the integrable evolution. Any contribution will be higher order. So this is already very different from what we saw for the BBGKY. So here I will do something brutal, so I will replace the 3-point function with the Kubo diffusion. In general, we know that this is not true, meaning that we are losing some contribution. There are some other contribution adding here, but for sure this approximation will give the correct thermalization timescale. At the end, the kinetic equation will not be full. We will lose some contribution, but it will be at the same thermalization timescale. So these are still okay. Okay, at this point there are some few steps. You can now solve this equation assuming that the density is constant. So you can solve this equation, put it here, and find the kinetic equation only for the density. And in particular, you can recast it in terms of quasi-particles. So you have only one equation with some rapidities that is looking like that. You will have a term that is factorized depending on the interaction, and then a function of the density and of the diffusion matrix. So here what we did is to consider a hard-earth gas and to write this equation for the hard-earth gas. So what I did is to solve this couple set of equation, in this case, with the potential that is decaying with the 6th power. We solved it with a bunch of different parameters, scaling time with the expected thermalization time coming from the kinetic equation. And what we found is that all these schools more or less collapse in the in the same curve. And also, since here I'm plotting the kurtosis for the rapidity distribution for the system, we see that this is going to the Gaussian distribution, that is the expected thermal distribution. So we can see that this set of equation finally is thermalizing. And it's thermalizing with a time scale that is proportional to the square of the integrable interaction. A is the length of our rods, so must be considered as the integrable shift. And then the square of the long range interaction. And crucially, this is the same scaling that they found in the experiment. And okay, here I also solved the kinetic equation, and again we found in this case perfect collapsing on all the function. So let's assuming what's the difference between the generalized BBGKY and the standard BBGKY. If you want to observe thermalization in the standard BBGKY, you need to consider interaction between two particles that will create a two-body interaction. This is not enough, you need a body interaction. So this correlation function must scatter again due to the long-range interaction to create three-body interaction, and then relapse. So it involves 2 times the interaction due to this weak V of x. In this other case, the two-body interaction, the two-body connected function must be created again in the same way due to the long-range interaction. But the three-point function can also be created in another channel due to the integrable scattering. But again, the integrable interaction is not a small parameter of the theory. It can be as long as you want. So this is the reason why we can see this difference in the thermalization timescales. And eventually, if you tune this parameter A to be big enough, this system can thermalize much easier.
Okay. So you still have ordering of the correlation. I mean, the higher point correlation scale, yeah, which is different from standard BBGKY, or?
Yeah, it's different because in standard BBGKY, the endpoint function is toward V at n minus 1, yeah. But here you can have
one over L,
yeah, this is 1 over L, and then on top of that you have correction in V, so then you have plus V squared and so on. Yeah. But if the system is homogeneous at the beginning, you have the first correlation is toward the V,
yeah,
and this is changing everything.
I see. Okay.
Is there any indication that there's some like qualitatively different physics that you get if you include higher levels of the BBGKY hierarchy? I see that this thermalizes, but like, yeah, you know, could there be important physics you think in the 4th and 5th level? Or?
Yeah, no, sure. No, of course, you are for sure losing something, and you're losing the dynamics of higher point function. So you're losing somehow some collective effect. To be honest, I don't expect to see like a huge difference in the evolution of 1 point function. Yeah. It will be much smaller, for sure. So like the difference will be like for sure smaller in the same way as the correlation function is smaller than other functions. So if you want to be extremely precise, then you need to include also other functions.
Yeah.
And also another important difference is that BBGKY is a microscopic theory. Here we are doing hydrodynamic. So, we also checked it against some numerical simulation of our system. So again, we took hardened gas because it's easy, and we simulated it with some interaction potential with the with the potential decaying gas X at the 6 or in a cubic way. In both cases, we see that this hierarchy is capturing pretty well the dynamics of the system. Here I also plot the standard BBGKY because one can also say, okay, just let's neglect integrable interaction, see what's happening, and it's completely off. And again, for the kurtosis, we can see that this is decaying to the Gaussian state, but it's still very slow, as expected.
Do you know how Boltzmann equation compares? Like whether it's better than...
No, it's terrible.
It's terrible.
Yeah, like this kinetic equation, I see like that. This kinetic equation are giving you the thermalization time scale, but they are completely useless because you're losing the initial time evolution. So you're starting like off from here. if you compare it with the final time, maybe with one fitting parameter, maybe they are giving something reasonable, but if you compare with it, it would be completely off. And here is also interesting because we can see some kind of pre-thermal state because, for example, if you observe some observable like the kinetic energy, you can see that these relax. So you can reach some state where these observables almost don't evolve, and it's really slowly decaying to the thermal state at the end. And this theory can also capture the evolution for two-point function, for example. We also tried many different other parameters with both in attractive or repulsive long-range interaction. In both cases, the small time evolution is well captured. So, yeah, thank you.
So, if I understood correctly, I mean, your integrable component is just a hardware system, is that correct? Or, I mean, so the other integrable component which we could take, I mean, basically the only other choice is the Coloscher 1 over sin squared interaction, right? I mean, that's a bona fide fluid. And so I just wondered whether you ever looked at that particular case.
I think I didn't understand the...
So you take as integrable component the hardware gas.
Yeah.
I'm saying that if you want to have an integrable fluid in one dimension,
Yeah.
the only other choice is the 1 over sin squared Coloscher fluid. That's a bona fide integrable system. So one might try, you know, I'm just asking whether you could try.
No, yeah, we didn't try yet.
This particular case.
But this, just an example, you can do it for any interval.
Yeah, you... Yeah.
So going back to the experiments, you had this formula for the thermalization time. There was coefficient of the integrability breaking term squared, and there was also coefficient of the contact interaction squared. That second thing is maybe less intuitive. Why it goes like so? G1D you can treat exactly right. U is the coefficient of the integrability breaking term. That's right.
Yeah.
Yeah. So you're working exactly in G and perturbably in U.
Yeah.
Yeah. And so I guess it's pretty intuitive that there's a U squared, but the fact that it's G squared is maybe less intuitive. Is there an intuition?
Yeah. Okay. Why we got this G squared, if you want, is because at the end the kinetic equation will be linear with the diffusive constant that is proportional to the square of the
You can show me your picture and you see.
Yeah, if you want, each of these interaction will bring a squared factor of the interacting parameter. So here you have V square, at the end you have V at the 4. Here you have V square and like integrable interaction squared.
So the G squared is the leading order in G, but you also have all order in G. Interaction.
So
The G squared is at small g, or it's exact in G?
no, it's exact in G.
It's exact in G.
Yeah. Well, then you will have other contribution.
So it's leading.
Yeah, it's yeah.
Okay. It's the leading order.
Yes, the leading order.
Another quick question. I mean, the BBGKY hierarchy, you know, has sort of one disadvantage that, you know, you have to go to, you know, further and further orders, even if you do just the kinetic limit. And then people have tried whether, you know, instead of correlation function, you look at cumulants. I mean, is that something which you ever tried in your context?
No. No, because I don't know. We are not using cumulants at all. We are always starting from microscopic dynamics for a single point. We are never using the full distribution function.
No, but I think Albert's saying that instead of doing a hierarchy for the correlations, you do the hierarchy for the cumulants.
Hierarchy for cumulants.
But I mean, no, here these are connected correlations. I don't know if that's what you mean by cumulants.
Maybe that's sort of what you're actually doing, right? I mean,
Yeah, it's what Leonardo was saying, that you have to subtract the divergent part. So you have to basically organize them in a way that
maybe
it's
it's cumulative, doing a cumulative expansion rather than.
This is important because otherwise you cannot truncate the hierarchy.
So the final state is a grid state, is it? Is it usually? I mean, when you say thermalization, is it that the final state?
Yeah, the final state. Yeah, what I mean by thermal state, I mean here that the final state has a Gaussian distribution of rapidity density.
But finally, it's like e to the power minus beta h, right? So
Yeah.
that's that, okay. And the idea is like if you do naive generalized hydrodynamics, then it wouldn't work. But if you include this extract term from this next order BBGKY, you get a better. If you just did naive GHD with this extra potential.
Yeah. Like if you want, this is naive GHD with extra potential.
Oh, is it?
Yeah. There's no other like naive GHD, because if you write naively like GHD with a force, and the force is the mean field force, here in homogeneous this is vanishing.
it will happen nothing.
Yeah, you will have like a steady state.
And one other question is like if the integrability breaking was a bit strong, let's say, then then one should expect normal hydrodynamics to work, right? Is that like I can imagine in an experiment it's easy to break integrability in a strong way.
Yeah.
Then isn't it that just normal hydrodynamics?
Yeah. No, okay, I got what you mean. Yeah. Okay. Here you have this is the mechanism to thermalize. And here I show this one, but this is still present. So if you slightly switch on the integrable interaction or like make this long range interaction stronger and stronger, then this one will be the fastest way to thermalize. So this one will be again the favorite way to thermalize, and you will find again this part.
But I think Abhishek is referring to the fact that, so here we only studied the homogeneous case for now, okay? So you have a homogeneous system, there is no hydrodynamics, but you ask what happens if you have this extra interaction, so you see thermalization. Then of course, your question goes beyond, like if you do a non-homogeneous system and you study how they spread, then you should see a transient from generalized dynamics to conventional dynamics, that we don't know.
Okay, if there are no more questions, let's thank Leonardo again.